Yeah. Well, so it's one of those days. We're highly caffeinated. It's a Monday.
It's Quantum Monday.
Yeah, that's right. And look, I think let's there's a lot of misinformation, confusion, nonsense swirling around about the quantum world.
Right.
And I think sometimes you just got to revisit the basics so that everybody remembers what's important.
Okay. All right. Well,
so we wanted to do some Q&A today, based on various like popular search terms, or I think a common question we got from going to the conferences was, okay, I get that Bitcoin is not quantum secure. How do you know that your thing is quantum secure?
Yeah, how can you build something that's quantum secure if there's not a quantum computer that can even do the hack yet?
And this is a great question. I think most people, if they're not computer scientists, this is a very natural question. Like, don't you have to test it with a physical computer? And yeah, of course, the testing with a physical computer is important, is sort of proof that you can do it. But most algorithm analysis, not even talking about quantum, just normal computing, most algorithm analysis is not done by running it. You can analyze the runtime of the algorithm, and there's a bit of an art to it, but it is actually a scientific thing of, okay, as the size of the input increases, how fast does the runtime increase, or like space usage increase? Like you use more resources if you run it on a bigger problem. So how fast do those resources? Does the resource consumption grow? All
right. I got a little lost. So
what
me out here. Yeah.
What I'm saying is that computer science is basically a branch of mathematics. It grew out of mathematics. It was, Alan Turing was basically the inventor of the computer, but it was a mathematical model for like, how do you formalize the idea of doing an algorithm? So before there had been attempts to do that sort of thing, but he's like, okay, what does it mean if you do a computation, like you remember you learn in school, you say like, okay, I'm going to, how do I divide one number by another? Or like, how do I multiply two numbers? That process is, it's a kind of recipe, or like a system. You apply the steps until you're done, and then you get the answer. And so, but for a long time, that was kind of like an informal idea. Alan Turing formalized that idea to make it precise enough that you could then get electronics to do it. Like understanding whether this algorithm does this and how fast it does this is not generally done empirically by running the hardware. It's generally done by analyzing the algorithm.
Okay.
So, and there's a systematic way to do this.
So I feel like there's like a certain level of like trust that you just have to have in engineers and developers and coders to say like, yeah, this is true, right?
I mean, to some extent, the things, it's not that you can't test it with hardware. It's actually pretty straightforward to test this. You could ask GPT to generate a code that demonstrates that, this algorithm is n squared as a complexity class.
Okay.
Meaning you could sort of graph it, for various inputs, and you would see that, the runtime increases like that. So yeah, I mean, I guess if you don't want to get into this stuff yourself and check it, then yeah, there's a certain amount of trust involved, but you don't have to have a super high level of technical skill to be able to check it.
Okay.
It's just that's not the most rigorous or most efficient way to do the analysis generally.
Right.
So anyway, so the point is that we have very precise mathematical models of how the quantum computer will work. So we don't need to build it first to be able to analyze the algorithms.
Okay. So we can kind of understand how they will operate when they reach scale. Is that an accurate statement?
Yeah, exactly. Because we already have algorithms for quantum computers. We're not waiting for the quantum hardware to develop the algorithms. We already have them. And the algorithms can be simulated on on classical computers.
Right. And they have like a limit because it's a simulation, so they can't quite get where the quantum computer would take us.
Exactly, which is why we're building quantum computers, is so that we can have,
we know, this is possible. For instance, I don't know, you have some example of like what might be possible at some point that isn't today?
Like everything the quantum computer can do, a classical computer can do. The difference is in the speed for certain problems. So it's not, certain, like factoring very large numbers can take a very long time using classical methods, but using a quantum method, it can happen very quickly. But it's still possible in both cases. It's just that for a certain size of problem, it clearly differentiates the two approaches. So it's just sort of like, you could compute SHA-256 by hand using pen and paper, but that's a really inefficient way of mining Bitcoin. And it's so inefficient that nobody would do it. And Bitcoin wouldn't even exist if that was the only way to do it.
Right.
So there are these like vast amounts of new applications that will emerge from quantum computing because certain things suddenly got much easier. But it's a natural question. But the answer is, like, we already have the algorithms, we have the software, we just don't have the hardware.
Okay, so the hardware is like, I think of it like bits. Like I remember some computers were 64 bits, and then it was like 128. This was like the processing power, and then it went to 256, and then 512, and then we got into gigahertz processors, right?
Sure,
It kept getting like smaller and faster, right? And then we could do more with those computers. In the beginning, we could just do really basic games, and then all of a sudden we're doing like, rendering 3D models and, editing video and doing things that we couldn't do on the computers when I was really young, and now I can. And that's obviously a lot of pieces improved, but a big part of that was the processor, right?
Yeah, definitely. It's there's so many pieces that go into these things, but like, I think, any engineer should tell you, like, the size of your debug loop, is sort of like how long it takes from I try something and I test it and I found out whether it worked or not. Like, does that take 1 minute? Does that take 1 second? Does it take an hour? That makes a huge difference in your approach. The longer that debug loop it takes, the more you have to like double, triple check your own work. The more you sort of start building other tools to kind of like pre-check,
right,
if you can. And that's what like compilers are, basically a tool like that. But once the loop gets small enough, then you can start to be more creative and just try stupid things that might actually turn out to be really novel and valuable, but that you would never try because you have to try maybe hundreds or thousands of iterations before you find it.
Right.
So in some sense, it does come down all to speed, frequency,
Okay, so we're talking about quantum computer scale, hardware reaching scale. So eventually we'll get into a place where this hardware gets way more powerful. Right now there's like a limit because like quantum computers are very sensitive, right? They can't have EMFs. It has to be cool. So there's a lot of room for error, and that's why it hasn't reached scale yet. Is that what's happening? Is that?
Yeah. I mean, I think looking at, you can look at it from like a physics point of view, and but from an engineering point of view, the central problem in quantum computing is reducing the error rate. You want to stabilize it so it's predictable. That's how you build a technology. You want it to be, you want your input to reliably translate into an output. And the more unreliable it is, the less useful it is. And
we can't trust it. It has to be consistent.
Right. Or maybe you need an expert and you need like to run it. And then you need, because you think about your laptop, like grandma can use a laptop. Can grandma use, one of those old computers that IBM used to make in the 50s that took up a room? Like, no, grandma probably can't do that.
Sure.
So this, the usability is directly related to the predictability.
All right. So one thing, I have this thesis about, people are like, oh, quantum, we're way far out. And I've heard this for 10, 15, 20 years. People are like, oh, we're 10 years out. We're 10 years out. Well, it feels like we're kind of at the 10-year mark here. And we've seen billions of dollars being invested from governments, private sector, venture capital firms.
Yeah.
Tons of money is being poured into quantum literally every month. We have a subscription with the Quantum Insider, and so we get to track all that. It's beautiful software that kind of just dashboard that kind of shows us the whole marketplace. And so I tune in there once a month, and I see literally hundreds of millions of dollars every month is going into quantum. So I look at that as a market signal. I think, wow, if I'm looking for any signals of something about to change, it was not the case 5 years ago. People were investing, but in the past few years, it's increased exponentially. So this, to me, is a market signal that maybe people are bullish that someone's going to crack the code and we're going to reach quantum scale soon.
Yeah, it's one of these things where, whoever gets there first has a big advantage, a bigger ROI than whoever gets there second. but not necessarily. I mean, really, it's, a lot of these things are about follow through. You think about like Facebook versus what was MySpace,
Right.
MySpace had their first mover advantage, but then they kind of stalled out at mid scale.
Yeah.
And so I don't know. When I look at the sort of various options of approaches to building a quantum computer, the one that makes the most sense to me is photonic computing. The using light. Light is one. It's the easiest way to see quantum effects. You can put a laser in front of you take dental floss and point a laser at it, and it'll split. And it doesn't split into two. It creates an interference pattern. This sort of and so you can see this sort of wave-like behavior from light. And likewise, you can play with polarized sunglasses to kind of experiment with how you can take the polarization of light as a kind of qubit or a computing platform. And so because it's sort of easily accessible from sort of meat space, something tells me that that's going to be the most reliable way. Also, it's very once you have the light, it's very low maintenance. It's not like a material that you have to manufacture, right?
Right.
I mean, obviously there's lots of materials in the computer, but there's something very lightweight about it. So that's so that would be if I was into investing in quantum hardware, I would put it in photonic computing.
Got it.
So that's just my guess, intuition.
Yeah. Obviously, this isn't financial advice, but we're looking at the future and everybody's looking for some alpha or where the next thing might be, and so we're investing in quantum security, right?
Right, which is the other side. It's well, look, I don't know which of these motherfuckers is gonna win this thing, but I know that somebody's probably gonna win, and we're gonna need protection against it.
Right, and that kind of brings us back to the first point that we were making, that we don't need that quantum computer today to build the protection for tomorrow.
That's right, exactly. So we can analyze algorithms under the sort of a mathematical model of the quantum computer. We can sort of essentially simulate how the quantum computer would behave for this algorithm and detect whether is this is it feasible for a quantum computer to crack this, because cryptography is based on all these sort of there's always this sort of asymmetry or kind of energy barriers where it's it's easy. You imagine it's easier to knock something off the table than it is to put it back on the table, right? Or it's if it's easier to smash it into pieces than to rebuild it, right?
Sure.
So life is full of these things, and so when you're building cryptographic systems, you use functions that have that kind of asymmetry where it's very easy to make it go one way, difficult to make it go the other way, and so the question is it actually difficult to make it go the other way? Oftentimes that's not fully proven. It's sort of assumed because of various things, but computer science is an incomplete field. We don't have proofs for a lot of the things we wish we had. And so, for example, we don't have a proof that it's hard even for a classical computer to reverse an elliptic curve private key from a public key. We don't actually have a proof of that. We have lots of reason to believe it. But that whole system has an algebraic structure, and you could make an argument, okay, when you do this, you're losing information, but that argument hasn't been sort of formalized well enough to. I mean, there's an open problem called does P equal NP? It's a millennium problem. If you solve this, or even make significant progress to solving it, you can get $1 million. And
who offers that bounty?
The Clay Institute.
Okay.
So it's basically just kind of like a university.
Uh-huh.
And so the idea is that this is something quite important, but we've built all this all this cryptography and all these computer systems on top of it,
right,
based on this thing where we don't actually have a proof that P doesn't equal NP. Meaning,
right, but no one's cracked Bitcoin.
But no one's cracked Bitcoin as far as we know. So that's and if they could, they would get really,
a huge reward.
Right.
Right.
You'd get billions of dollars for cracking even just one key.
Right.
So, we walk around this conference and I think a lot of people don't even realize Bitcoin is not quantum secure. It's that's sort of the basic question that is still being navigated by the public. And I see a lot of, quite frankly, misleading or outright false posts on Twitter,
Yep.
on X about, oh, don't worry about quantum. Bitcoin is already quantum secure. I've seen many posts like this. And I just wonder, is this somebody like just trying to protect their bags? Like, they're like, oh, I bought Bitcoin and I want to protect it. Or is this like, hey, me and my boys are working on a quantum computer. We want to make sure we maximize our advantage with it by don't upgrade your systems because, we want to keep everybody weak and vulnerable.
Right.
So because it's just like you don't have to scratch very far beneath the surface to discover no. Like this is not a mystery. This is not like it's not controversial in the world of computer science.
Right. Math is kind of straightforward. That's the beauty of science and math, right?
Yeah, I think math even more so. Like you have a proof or you don't. The science, it's more like, okay, you get evidence and it crosses some threshold of, sort of proof, until there's a better theory. But like with math, everything is rigorously defined. So then, it's not to say that people don't think things are proved sometimes, and sometimes it turns out to be false. People, make mistakes. But like the elliptic curve signature scheme that Bitcoin uses is not just quantum vulnerable, it's probably the most vulnerable algorithm that exists in terms of it's the most quantum vulnerable algorithm that exists. So like that and factoring large numbers, which is RSA, which is another popular cryptographic scheme. So it's kind of weird that we've somehow like there's all these problems like computer science problems, and most of them are sort of like somewhat affected, but maybe not that much by quantum computer. Like there's the traveling salesman problem or searching an unsorted database, these sorts of things. But they don't get they're affected by quantum computing, but not that much. But there's a few problems that are like destroyed by quantum computing, and it just so happens to be the ones that we're using for all our cryptography. It's a little like, is that a coincidence? I don't like.
Yeah, it's quite a vulnerability, and now with it becoming so popular, now it's like we're talking about the U.S. government is like talking about using Bitcoin as a reserve, right?
Right. They have one part of the government saying, let's use Bitcoin as a reserve. Another part of the government is like, hey, everybody, we need to swap out the elliptic curves ASAP.
Right.
And
well, you're talking about like NIST.
Yeah, exactly.
Right.
So, but then also, there's all this talk like, okay, if you read BlackRock's, ETF docs, they have discretion on picking a fork. So BlackRock could probably at this point force a fork of Bitcoin and say, and they might use quantum computing as the excuse to do it.
Interesting.
Like we say, hey, you guys need to upgrade this.
And now, and this is just like we're going on a different rabbit hole here, but just as we think about like decentralization, and it's like, wow, BlackRock's got a big stake in this thing. And anyway, yeah.
No, I see it through the lens of like Animal Farm. That book. It was quite impactful on me as a child. But it's like, the animals overthrow the farmers. Okay, good job, guys. And now, now a different set of animals becomes the farmers. And it's sort of like, oh, cool, you like killed that dictator, and now his number two, is now in charge, and he's just as bad or worse. And so it's like, it's not so easy to just wave a wand and like change the structure of the world.
Right. All right. So post quantum cryptography, what are the main challenges for developing these algorithms?
Well, look, I'm not an academic. I'm not a professional cryptographer. I'm more of an engineer. I'm using things that were developed by other people.
Okay.
But the big challenges with developing any cryptographic system is that there's no like playbook that tells you exactly whether this thing is secure or not. And that's sort of what the P equals NP question is about. Like, okay, is there some sort of like deterministic program we could run on an algorithm and inspect it and say like, okay, is this secure or not? We don't have that. And so it ends up becoming more of a trial and error thing where it's like, okay, I think this is secure. Everyone try to break it. And then everyone tries to break it and someone finds a way to kind of like maybe half break it. You're like, okay, because it's like, okay, we know ways to find the keys, but it takes a really long time. That's sort of basically what cryptographic security comes down to. It's like you could search through all the possibilities and eventually find it, but it would take you, 1,000, 1,000,000, trillion years, whatever the number is.
All right, I'm gonna do like a really basic analogy here.
Sure.
Like if you had like a safe and you were gonna like crack the code and it had like, I don't know, maybe 10 digits.
Right.
Was the safe code.
Versus if it had 3 digits, it was like, okay.
I might be able to sit there and figure it out.
Right. Like if it has 3 digits, you could try every single option. If it had 10 digits, it would take you possibly more than your lifetime to do it. So then it's not practical. Now, the question is always, is there a better way to do it than brute forcing it? Meaning trying every combination. Is there some sort of structure that you can exploit? And so, in a physical safe example, a lot of times if you maybe you listen very closely or you have a specialized instrument, you can detect that something inside clicked when you pass the right number.
Okay. So now you've narrowed it to this maybe 3 or 4 numbers.
Right.
Like, I know one of them is in here.
Exactly. So now you've narrowed the search space. It's no longer try all combinations. It's try like 3 combinations for this one and 3 for the next one. So now instead of being say 60 to the 10th power, it's like 3 to the 10th power. So still a lot of combinations, but so the same thing happens in cryptographic algorithms, is that you can have they generally have some kind of structure to them, and that structure can be exploited. And proving it can't be exploited, in some cases you get stronger evidence or stronger proofs. In some cases you don't. But it's kind of like an arms race sort of thing. You want to build up your algorithms and you want them to be secure against the enemy. But it'd be nice if we had a back door that only our guys knew. But of course, once you put a back door in it, then the bad guys, the other side, the team that you're playing against is also likely to find that back door.
I guess we could talk about NIST maybe a little bit, and how it kind of came to be, because you chose to use dilithium, right?
Right. So there's
for our project, right?
That's right. Yeah.
So Quantum is using dilithium, which is a form of post-quantum cryptography, right?
Right. So there's many different approaches to cryptography. There's different sort of subcategories. So elliptic curves was one kind of subcategory. Lattice cryptography is another. There's there's isogeny based. There's all these different.
So dilithium falls under lattice cryptography.
That's right. It's using the mathematics of crystals. So if you kind of imagine that there was like a like a crystal is like a physical structure that has a very predictable structure. So it's sort of like every layer of the crystal is very similar to the previous layer. So that regularity is what gives it this beautiful symmetry and makes it very pleasing to the eye. But
you use crystals for cryptography.
Well, okay. So I'm talking about that's the physical object, the crystal. But if you sort of abstract that into a mathematical structure, and then now it's abstract, so we could have it in not just 3 dimensions, but we could have it in say 256 dimensions. Then you can start to talk about, imagine like a very high dimensional crystal, and we're going to hide information in the crystal, or we're going to sort of, and there's multiple ways to describe this crystal, but some of them are more efficient than others. So like in lattice cryptography, generally there's like a good basis and a bad basis, meaning like there's a kind of like a way that will technically get you where you want to go, but in a very kind of like roundabout, inefficient way. But it's still technically a correct map, versus a much smaller and more accurate map, or sort of more efficient map.
Right.
And so that asymmetry becomes the sort of public-private key. That's the energy barrier or the trapdoor function. And so that's just one example. There's a lot of different kinds of cryptography, and people in universities who are specialized in this have studied these things it's a pretty small group of people, to be honest, but it's like, I've studied these things for decades, and each one has its own strengths and weaknesses. And there's cryptography, which is this, how do you secure the thing against being, read by an adversary or impersonated, modified by an adversary. And the other side is cryptanalysis, which is like, how do you sort of analyze the behavior of the algorithm to try to extract the private key from the public key, or extract a secret from. This is very similar to, like, say, timing attacks in like physical devices. So a lot of people don't realize this, but let's say you have a hardware wallet. Well, you can, if you have a very powerful antenna and you're close to it, and you can do many recordings of signatures, many times the differences in how the electromagnetic waves come off of the thing will give you enough clues that you can start to reconstruct the key.
It's just like, just like on that safe, right? It was like,
exactly.
I'm getting closer. And that would be like somebody in proximity to you. Like that would be
probably funny. Or, this is why I don't really trust the sort of these trusted execution environments. Because they say there's a secure enclave. It's a separate chip, and there's a secret on that chip. But like usually people deploy these things in like a data center, and there's like all this hardware that's sitting right there next to it. And are you sure that there's no information leaking out of there? I mean, there's this whole strategy in writing cryptographic algorithms called constant time. You write the algorithm so that it takes, like every function in the algorithm needs to take exactly the same amount of time regardless of its input. If you can tell that the algorithm's taking less time or more time based on the EMFs it's giving off,
right,
then you can start to figure out, okay, well, that time it was a 1 and that time it was a 0. And
right. So if it did it really fast, then I know I'm in this little range. If it was longer, I might not really have a whole lot to guess from there. But
well, sure. I mean, sometimes you get more information on one side than the other. It depends. It's highly dependent on the specific situation. But the protection is to make it to increase the anonymity set,
keeping it consistent.
Every call to the function is exactly the same amount of time.
So you have to like add extra stuff on to the short stuff.
So it means you end up doing roundabout things that you normally wouldn't do.
Okay.
It makes the code slightly less efficient.
Yep.
But it's more homogeneous. And
that's cool.
It is pretty cool. And this sort of analysis can happen at different layers of the stack.
Okay. I got more questions.
Okay.
How do I be safe, man? You scared the shit out of me. Like nothing's fucking safe. Like what do I do? Like what the fuck?
Well, okay. So there's one is, I mean, if you're an engineer, you have more control over it because you can choose which cryptography you're using. So like a simple thing, if you're running a website, you could use TLS 1.3 that supports the old algorithms and the new ones. So then if people's browsers support it, which so that's something that users can do is use a browser that supports TLS 1.3. Now, realistically, like your browser connection is not going to be the first target to someone with a quantum computer. But it's sort of it's a way to signal socially that you think it's important. So then that makes it more likely for other people to implement it because it's kind of like a herd immunity thing. Sure. There's a lot of cryptography deployed all over the internet, and basically all of it needs to upgrade. And it was a huge fucking push to get from HTTP to HTTPS everywhere. And that was, I'd say Snowden had a huge hand in making everybody realize that widely deployed encryption is important, but that took a big push, and this is going to probably take a similar size push, if not bigger. And a big part of the issue is that if someone has a quantum computer and they don't reveal it, if it's say they developed it in secret and then they crack keys, it doesn't really leave a trace necessarily.
Oh, I see.
You just know, like, you might not ever find out that someone cracked your keys. In the case of Bitcoin, you would probably just see somebody lost a lot of money. But was that because they got hacked? Someone got into their phone? Someone got into the multi-sig? There's a lot of plausible deniability in there. So what can people do? There's out of the box, like the cryptography has gotten to the point where it's like fairly easy to just swap out the old one with the new one. Now, there's some hiccups that happen there because a lot of times people have hard-coded certain like maximum message size or something like that, and the size of the keys in say lattice cryptography are much larger, so they sometimes spill over these assumed bounds. So there's like, in TLS connections, there's a handshake where you're like, okay, we're going to establish a shared secret, and then we're going to use that to efficiently encrypt or authenticate our communications. And that handshake is sometimes there's, a server might just assume, okay, that handshake's always going to take less than this size, but now it doesn't anymore. And so now you got to go like dig around in some kind of like ancient code that no one's seen for decades, and then like go upgrade that thing. Of course, it probably doesn't give you a nice log either, so then you really have to dig to find it. So that's the sort of like but it's very like kind of standard engineering work. There's nothing really miraculous about it. It's more just like patience and digging through shit you don't understand. So yeah, I mean, one of the things you can do is like, I don't know, you can call your crypto exchange up and be like, hey guys, are you using post-quantum cryptography, or like, what are you doing about the quantum threat? I think the pressure has to come from somewhere, and people, especially businesses, are mostly responding to money signals, right? So if it seems to them that their customers care about this, then they're more likely to prioritize it. If you wait for the government to tell you it's important, it might be too late.
And how can people get involved with Quantus Network?
I would say come to our Telegram, ask questions. Our coin's on testnet right now, so you can mine it. It's not worth anything. Please don't spend a lot of money doing it. You can also download our wallet. It's on test flight. You can play with it, and we've got reversible transactions. You can sort of feel what it feels like, and actually it feels pretty similar to existing things. It shouldn't be any harder, if it's implemented correctly, which
it's really cool, the reversible transaction, actually, because you can't even do that with Zelle or a bank transfer or I don't know, PayPal. If I send you something, it's kind of done, and then if not, it's a real pain in the ass. I got to contact the company. I got to
get the card company,
whatever it is,
call the bank,
file a claim, whatever,
right. And so we can program all those people out of a job, but it's also like, once we kind of reach the next step with that, which is, you set a third party to be your reverser, then that's, we're kind of reintroducing trusted third parties, but you get to pick your trusted third party. Because, the original Bitcoin white paper was like, okay, we're cutting out all the trusted third parties. And then, we have all these centralized exchanges that hold your money for you. There's Bitcoin ETFs and there's Coinbase. And so why is that? It's because most people actually do want a trusted third party. Okay, so why don't we make it so that you can have a trusted third party if you want? It's optional, and you get to choose which one it is.
That's beautiful.
And so that's the model we're running with.